Welcome back, this is your Ramanan. In the last section we evaluated our sign model in Python, and now comes the exciting part. Bringing the model to life on an embedded device, which is Arduino Nano 33B license. So this slide is about building a complete application with TinyML. A trained model by itself is just numbers. It can't sense, it can't act. What makes it powerful? So wrapped inside application that interacts with the real world. This makes it is a powerful application. So on a microcontroller, this application needs to handle three key objects. So one is to provide input to the model either from a sensor or a simulated values. So second is run inference. That means executing the model efficiently using the TensorFlow Lite. Third is handling the output. Here we are going to talk about the blinking of LED. We can also add as a controlling a motor or logging predictions or also a graph output, a visual graph output. So think like this, training the model gave us the brain, now we are building the body around it so that brain can actually do something for itself. Alright, let's move on and talk about the why model by itself is never enough. So here is the big idea, the model alone is never enough on its own. It's like having a calculator chip but with no buttons and no screens to show the answer. So what we need is a working TinyML system is 4 parts: input, interpreter, software, hardware, and for us to show the output. So to actually use the model we need this full program. So this is what makes the machine learning practical in the embedded system. So input must be sensor data or signals to feed into the model. Interpreter, we can use the TensorFlow Lite, which actually runs in the model on the tiny hardware. Software is, we are going to use the C++ code that ties everything together, and hardware is this Arduino Nano 33B license, and the output is in the hardware we are going to use this LED. You can also use the motor or the display to show this sine wave. The input will be the simple x values which we are using it to create this sine wave. The interpreter is a TF Lite micro. The hardware is, as I said, Arduino Nano 33B. So remember, TinyML is equal to model plus software plus hardware, which makes this whole system possible. So this is the application code. We can see here we are getting the sensor data and training model with this, both of them inputted into the code, and then after that we are processing, and output is in this device, which is LED, or we can use the motor display as I said. So let's see what exactly we are going to build. Let us be clear about what we are building. In our application it will be written in C++, which is modern C++ but still efficient for microcontrollers. The structure is similar to Arduino sketches: a setup function that runs once to initialize everything, and a loop function that runs forever, calling the model repeatedly. So the program will feed the values to the model, run inference, control a visual output like LED. This is the first of a real-time TinyML application, compact, elegant, and entirely C++ 11 based. So each loop iteration, we are going to talk about the loop iteration. So each loop iteration, the program will generate the next x value in a sine wave, then run inference to predict the y, which is sine of x, and the output result will be shown in the LED. Though this might look simple, but it actually a template you can reuse for any TinyML project. Just to swap the model and the sensor, you can pop out a new working model. So this displays a sine value from 0 to 2 pi, and this code we are going to use is very minimal. You can actually understand what's happening here. Moving on to look at the building blocks in more detail. For this whole application to work, we need to include several header files and CC files. So here we are going to talk about all those header files we are using here. Let me walk through these header files one by one. Sine model data.h. This file contains our trained sine model as a byte array. And next is microinterpreter.h. This is the engine that runs the model. Micro error report.h. handles logging messages, AllOpsResolver.h. This ensures that the operator like dents and relos are available. Microtest.test. This writes simple unit tests. Schema generated and version.h. ensures compatibility with the model format. We can think of this as a toolbox. Each include brings specific set of tools that we'll use to assemble our final program. Alright, before we flash this into our board, let's talk about testing. Minimal test app. So here it's an important best practice before running a code on a microcontroller. Always test it on your PC first. That's exactly what the file Hello World test.cc does. It uses a TF Lite micro test framework to check if the model routes properly. The interpreter can run it, outputs are valid. So these tests are defined with macros like TF Lite micro test begin and TF Lite micro test. So these keeps the test neat and modular. The workflow saves you time. You can catch runtime issues early on the computer instead of struggling with the device. In real world projects, this is a continuous integration pipeline. Test locally and then deployed globally. So thank you for sticking with me. In the next section, we'll move on to the setting up Git and understanding the project structure, mapping our model into memory.